Section 16.2 Nuclear Reactions. In the process called radioactive decay, a nucleus spontaneously breaks down by emitting radiation. This process is shown by writing a nuclear equation of the atomic symbols of the original radioactive nucleus on the left, an arrow, and the new nucleus and the type of radioaction emitted on the right. Radioactive nucleus yields new nucleus plus radiation alpha, beta, gamma, or beta positive. In a nuclear equation, the sum of the mass numbers and the sum of the atomic numbers on one side of the arrows must equal the sum of the mass numbers and the sum of the atomic numbers on the other side. Alpha decay. An unstable nucleus may emit an alpha particle, which consists of 2 protons and 2 neutrons. Thus, the mass number of the radioactive nucleus decreases by 4, and its atomic number decreases by 2. For example, when uranium-238 emits an alpha particle, the new nucleus that forms has a mass number of 234. Compared to uranium with 92, the new nucleus has 90 protons, which is thorium. In alpha decay, the mass number of the new nucleus decreases by 4, and its atomic nucleus decreases by 2, changing the element. We can look at writing a balanced nuclear equation for americium-241, which undergoes alpha decay and shown in sample problem 16.2. Beta decay. The formation of a beta particle is the result of the breakdown of a neutron into a proton and an electron, which is a beta particle. Because the proton remains in the nucleus, the number of protons increases by 1, while the number of neutrons decreases by 1. Thus, in a nuclear equation for beta decay, the mass number of the radioactive nucleus and the mass number of the new nucleus are the same. However, the atomic number of the new nucleus increases by 1, which makes it a nucleus of a different element. This is called transmutation. For example, beta decay of carbon-14 nucleus produces a nitrogen-14 nucleus. In beta decay, the mass number of the new nucleus remains the same, and its atomic nucleus increases by 1. Positron emission. In positron emission, a proton is an unstable nucleus is converted to a neutron and a positron. The neutron remains in the nucleus, but the positron is emitted from the nucleus. In a nuclear equation for a positron emission, the mass number of the radioactive nucleus and the mass number of the new nucleus are the same. However, the atomic number of the new nucleus decreases by 1, indicating a change into an element of another transmutation. For example, the aluminum-24 nucleus undergoes positron emission to provide magnesium-24 nucleus. The atomic number of magnesium, 12, and the charge of positron 1, given the atomic number of aluminum, 13. Gamma emission. Pure gamma emitters are rare, although gamma radiation accompanies most alpha and beta radiation. In radiology, one of the most commonly used gamma emitters is technetium. An unstable isotope of technetium is written as a measurable symbol M, isotope technetium-99M. Technetium-99M, or technetium-4399M, by emitting energy in the form of gamma rays, the nucleus becomes more stable. Figure 16.2 summarizes the changes in the nucleus for alpha, beta, positron, and gamma radiation. An alpha emitter radiates a helium atom or helium nucleus, and it becomes a new element. A beta emitter emits a high-speed electron becomes a new element with an atomic number 1 greater than before. A positron emitter emits a positron. It becomes a new element with an atomic number 1 less than the original. And a gamma emitter, the mass number is the same and the atomic number is the same, and it just makes the nucleus more stable. Producing radioactive isotopes. Today, many radioscopes are produced in small amounts by converting stable, non-radioactive isotopes into radioactive ones. In a process called transmutation, a stable nucleus is bombarded by high-speed particles such as alpha particles, protons, neutrons, and small nuclei. When one of these particles is absorbed, the stable nucleus is converted to a radioactive isotope, and usually some type of radiation particle. When a radioactive B10 is bombarded by alpha particles, the products are radioactive nitrogen-13 and a neutron. So boron-10. All elements that have atomic number greater than 92 have been produced by bombardment. Most of these have been produced only in small amounts and exist only for a short time, making it difficult to study their properties. For example, when californium-249 is bombarded with nitrogen-15, the radioactive element dubdenum-260 and 4 neutrons are produced. Technetium-99m is a radioactive isotope used in nuclear medicine for several diagnostic procedures, including the detection of brain tumors and examinations of the liver and spleen. The source of technetium-99m is molybdenum-99, which is produced in a nuclear reactor by a neutron bombardment of molybdenum-98. Many radiology laboratories have small generators containing molybdenum-99, which decays into technetium-99m radioisotope. The technetium-99m radioisotope decays by emitting gamma rays. Gamma emission is desirable for diagnostic work because the gamma rays pass through the body of the detection equipment.